wanted me to convert, and I was like, nah, I'm alright.
My friend converted to get married. She was really like, you know, she's about to turn 30. She's like, whatever religion is fine.
I'm not even a religious person. If I was like saying I was going to convert for a girl, my grandma.
Like, you want to marry me? We'll just do whatever. All right. So we're gonna so here's what we're doing. It wasn't Scientology, so I guess she dodged a bullet there. Do not join Scientology, guys. It does not have anything to do with science. Just FYI.
Hey, it's the world's greatest Ponzi scheme.
Yes, that's true.
Have you seen that Netflix show?
Oh God, it was like terrifying. No, the HBO one was really terrifying. Going clear. I had to stop watching it because I was just like, this is why?
Who fell for this?
Why is this a thing?
See, but like people are like, I don't understand why Tom Cruise is cool with this. I'm like, yeah, bro, but if you're like at the top,
it's good. If you're in a pyramid scheme, you want to be at the top of the pyramid scheme. You don't want to be the people being crushed on the bottom. My grandpa actually met with L. Ron Hubbard. Like before he started Scientology, they were like on a plane together or something, and he was telling him like he had this like really great idea, and I was like, that sounds that sounds awful, and he's like, yeah, I think I'm gonna make a lot of money.
I mean, it's a genius idea though, because like a normal Ponzi scheme, like the federal government's gonna shut you down, but if you claim you're a religion,
yeah. Well, I mean, there's plenty of like religions that have been doing it for years.
Right.
Hello, megachurch. So, just what Jesus wanted. Giant churches.
Hey, if I ever become a millionaire, I'm
built out of gold and crystal.
A church and a non-profit.
Oh boy. Okay, I have to
CEO
delete the beginning of this recording. So we're gonna go through this chapter. We're at about a chapter a day now, but these chapters are a little bit shorter. So we're gonna do this chapter today. On Monday, we will go through the next chapter, which is chapter 19. And then chapter 20 will be, I will record the lecture. You can watch it over Thanksgiving break at your leisure, okay? Because I'm going to cancel class on Wednesday, unless you guys want to come.
No.
I had enough people email me that said they couldn't come that I was like, you know, if half the people are missing the class, that's a fairly important chapter. So I'm going to have a video recording of it. It'll be like, you'll see the slides, you'll hear the voiceover, and then I'll try to work out the problems like you can see them worked out. And so this is actually like a twofer. The way we can get away with this, or the way I can get away with it canceling class, is that it's probably going to take me like 5 hours to record the 2-hour lecture, first of all. And the other thing is I want you guys to give me some feedback on the video because I would like to eventually develop more content that's online that you guys can access outside of class. And so I'm going to send out like a little quiz and / survey that you can fill out after you watch it. But it should only take the same amount of time you'd be in class, and then you can do it anytime that you want to over the break, okay? And then you got Wednesday off, so you can go buy your turkey and do all that good stuff. Anybody leaving town for Thanksgiving? No? All right. Well, I'm not either, but a bunch of people are coming to my house. My in-laws are coming with all of their dogs, so.
Oh.
What?
How big's your property?
It's like 6,000 square feet. It's not too bad. But no, it's just like the dogs are just like everywhere. They like you like turn a corner and there's like dogs. They're big, like it's like German Shepherd, a boxer, and then I have like a little like medium-sized dog. It's gonna be terrible. I tried to get them like an Airbnb that took dogs, but the prices had gone way up, and I was like, all right, fine, they have to stay with us. So anyway, my parents are lucky they got a hotel. All right, so let's talk about the thermal properties of matter. All right. So, microscopic versus macroscopic. Macroscale is objects large enough to see and touch. So when we talk about like pressure and force and volume, those are macroscopic quantities, okay? Microscalar objects that are too small to see with the naked eye. So when you're talking, so in terms of snow, right? Macroscopic is it looks like white paint all over the roof or whatever. And then microscopic is like an individual snowflake, okay? In terms of like gases, macroscopic is like, okay, the volume of air in this room. Microscopic is individual air molecules. Okay? So, talk about equations of state and the ideal gas. So that some of this should be a little bit reviewy if you've taken chemistry. State variables, that's just a fancy way of saying the variables that describe macroscopic systems. Remember, a system, how do we define a system? What's a system in physics? Whatever you say, that's right.
It's 100% true.
So you just set a boundary, right? So for instance, if you're talking about a gas, like let's say in a piston, the boundary could be the piston, the system is anything inside the piston, and then the environment is anything outside the piston, okay? So you just have to figure out your boundaries. That's a system, all right? So state variables describe macroscopic systems. So for instance, when we talked about the Coke bottle, the Coke inside the bottle was our system, okay? So that means we could figure out the volume of the Coke inside the bottle, figure out the mass, figure out the pressure, the density, the temperature, all of those things, okay? You can also figure out things like the heat, okay? So the definition of an ideal gas, it's a gas. It's a gas whose molecules don't really interact, except occasionally they run into each other, okay? But they don't, what we mean by they don't interact is some molecules are charged, right? So they could be attractive or repulsive. Ideal gas molecules aren't, right? They're basically just like, you can approximate them to be tiny spheres that just bounce around and fly around, okay? And if you're looking at the periodic table, where are your best ideal gases? Yeah, all the way to the right, that would be the noble gases, okay? Because those are all inert, right? They have full outer shells, so they're nice spherical looking atoms, and they just bounce around. And so those are all going to be monatomic gases. Then if you move over, you can get like the diatomic gases. What do we mean by diatomic? Two atoms, right? Two atoms stuck together, like any oxygen, right? Nitrogen. Those are all diatomic gases. So monatomic gases would be like helium, neon, argon, krypton, and not so much xenon. I mean, we don't really deal with xenon. Some of the higher ones. And then the diatomic gases are over just slightly to the left of those, okay? So, and then there's also like more atoms stuck together, and those get a little bit more complicated. We'll talk about all that stuff a little bit. Anyway, for an ideal gas, density is low, meaning there aren't a lot of molecules, so it's definitely a gas, and it's not near the condensation point, okay? Because if you're near the condensation point, you're about to become a liquid. That's not going to be as simple, okay? You're about to experience a phase change. So, state variables of interest, pressure. Now remember, P has lots of meanings here. P and rho are not the same. So P is pressure, rho is density. And then we have temperature, volume, and what's N? Moles, yeah. Okay. Question. Helium. But it doesn't really matter. Assume it's an ideal gas. 5, 10. Did I count that right? Yeah, there's 10 of you. I'm just missing one person.
I was like, which person is not letting?
Who is this person not paying attention? Oh boy, you guys are good. The other class had trouble with this for some reason. Good. So it would shrink. Yay! All right. And why does it shrink?
They're going to be like expensive or closer together. Yeah.
Why are they? Yeah, they move less, right? So if you're a hot molecule, what do? Yeah, look how everyone's acting it out. You're like whoa, all over the place. Okay. As you get cold, you kind of like start moving closer and not jiggling as much. And so the reason that when things move faster, they start to bounce off each other and then they expand. Okay. If you're not moving as much, you're not bouncing as much. You can contract a little bit. All right. So that's a microscopic thing that creates a macroscopic effect. All right. All right. Here's another question. Oh. Are you the chemistry lab partner?
Well, my lab partner did this. Like,
Oh, okay.
put a cork on
Right,
top
right.
of it, and I was like, it's heating up though. Where do you want the steam to go?
This is like when my roommate tried to cook with alcohol.
Oh.
And he put it in the oven without actually cooking the alcohol off first. And closed the door. It was awesome.
It was awesome.
Love your oven.
Yeah, like for being a military dude, like I'm inside my room, like playing my games, and then all of a sudden, like you just feel pressure change, and I watch all the curtains and stuff blowing, so I automatically know, like I roll over to the floor and fireball in the room. It was great.
My friend tried to deep fry fish sticks.
What the F?
He didn't let him thaw out, so he just put like ice fish sticks.
I also had a roommate in the army put his thermos in the microwave and tried to start that too.
Why?
Because like a lot of these dudes have never been alone before.
Yeah, they're 18 years old, you know,
Their parents have done everything.
on their
for them.
own. Shit on age. First time.
Did you vote this time?
Pretty sure.
Darwin.
I did.
All right.
I don't know who
It's somebody
There
else's
you go.
time. All right. Darwin. All right.
We're
You're
so
killing
smart.
it. Your lab partner is going to explode stuff everywhere. All right. And why? What are you increasing?
Pressure. Pressure has nowhere to go.
What are you increasing first?
Heat.
Temperature, right? Which increases pressure. The previous time, you're decreasing temperature. What did you change? Volume, right? Volume. Also pressure. But, so what we're seeing here is a relationship between temperature, pressure, and volume, okay? If you change temperature, you change pressure and or volume, all right? Because this is pressure, this is volume, number of moles is usually constant. For instance, in the balloon, the gas isn't getting out of the balloon, it's just staying in there. If you close a flask, the gas isn't getting out of the flask, it's just staying in there. This is a constant, this is temperature. We use slightly different units in physics than we do in chemistry. Just a word to the wise. Pressure is in pascals, okay? Pascals are newtons over meters cubed, which is force over area, meters, volume. Force over volume? No. Newton over meter squared, force over area, okay? This is volume, volume's in meters cubed, okay? N is in moles, R is this, it's joules per mole Kelvin, okay? And then temperature is going to be in Kelvin. And make sure that you do that, because remember, when we were dealing with change in temperature, you didn't necessarily have to convert back and forth between Celsius and Kelvin, but this is not a change in temperature, this is a temperature at a specific point, so you will need to convert to Kelvin. Yes? Ah, this is the Maxwell-Boltzmann constant. Yes. So this is the same equation with a different constant. So this is still in pascals, which is newtons per meter squared. This is still in meters cubed. This is now N, which is molecules, okay, instead of moles. So this is like the number of moles. This is the number of individual molecules, okay? This is the Boltzmann constant. This is still temperature in Kelvin. So these are the only real things that change. The difference is in physics, like a lot of the time you're dealing with such small sample sizes that the individual number of molecules matters, okay? This is for like a more bulk situation. This is for like a very tiny amount of stuff, all right? All right, so we're gonna just do like a really quick example that's basically just plug and chug. There's some varying people have different standard temperature and pressure, which seems non-standard. But for this case, we're just going to do temperature is 0 degrees Celsius, okay, which is 273 Kelvin. Pressure is 1 atm, 1 atmosphere. Of course, what do we need the pressure to be in? What units do we need it to be in? Pascals, okay. Does anybody know what the atmospheric pressure is in pascals? No, it's okay. You don't have to know it. So if we're gonna have a volume. Oh, we want to find the volume. So we have 1 mole of ideal gas. So that's N. That's 1.00 mole. Okay. Standard temperature and pressure. Well, the temperature is 0 Celsius. What is that in Kelvin?
273.
That's 273. Okay, and the pressure for atmospheric pressure. that's going to be 101 times 10 to the third Pascal. Very easy to remember, just like 1 atmosphere. It's not easy to remember, but write it down. Okay, so here's our pressure, temperature, number of moles. We have our constant, which our R is 8.31 joules per mole Kelvin. Okay, so that's all the things we need. Then we want to use PV equals nRT. We're looking for volume, so we solve for volume. That's nRT over P. So that's going to be 1 mole times 8.31 joules per mole Kelvin times 273 Kelvin times our divided by our pressure, which is 101 times 10 to the third pascals. Okay, and just to keep track of all these units here, we have moles, cancels with moles. We have Kelvin, that cancels with Kelvin. Then you have joules divided by pascals. Okay, anybody know what joules is?
With a unit?
Yeah, how does it break down? There's some kilograms. Newton meters, right? Newtons times meters, because work is force times displacement. So newtons times meters. Pascal is newtons over meters squared. Okay, so the newtons cancel. What do you end up with? Meters cubed. Okay, so the units work out, and that's why it's actually pretty good when you're not used to using the PV equals nRT with these units. Make sure your units cancel, and that way you know you plugged in the right things. Also, if you hadn't changed this to Kelvin, what would your answer be? 0. Okay, which doesn't make a whole lot of sense, so make sure you change it to Kelvin. All right, so this gives you 0.0224 meters cubed. That's the volume of 1 mole of gas at standard temperature and pressure. And part of the reason we do this problem is because this actually comes up a fair amount in the problems that we do in this section. Okay, this volume shows up a lot. So just sort of take a note of what it looks like, so you have an idea when you actually do these problems if your answer looks reasonable. Okay. All right.
Do you want us to memorize that pressure?
Yeah.
101 times 10 to the third.
I mean, you don't have to memorize it, but I'd write it on a cheat sheet. Yeah. I mean, memorize it, whatever. Do your best. I don't really like, I'm not really like into memorizing things. Like, it's not a thing I want to do. Okay, so I want you guys to try this problem. We'll take about 5 minutes and go over it. Physics isn't about memorizing, it's about solving. volumes over meter squared. Because pressure is force over area. No pressure. The pressure.
Because we have a volume. Dimension.
Yeah, 101.3
Pressure. Right?
pascals, right? So 1 atmosphere. This is atmospheric pressure. We know the volume is given, right? We can find it. For the temperature. There's only one thing we know.
Yeah, I got that. So that it's 200 degrees Kelvin. What's the molar? So it's like the. No, no, but what is it in the terms of variables? The molar mass is. Those variables. I would think it'd be. I think it'd be this guy, right? Isn't it? It's not the R. No, is it? It's not the R. We're looking for pressure, right? So we're looking for pressure. We're solving for. Well, so we have more pressure. It's the atmospheric pressure. What is it? Yeah. It's the 101. Oh, that's not. Oh, so we're looking for volume. But we're looking for. We're looking for. We're looking for. Oh, we have the volume. Oh, I see. We have.
I don't know.
What is it? Because I don't see.
Oh, so it's
Kilograms. Oh, no, we have R. No, is it R? There's joules. No, she gave us something for R. I don't know if she. What is it? Molar mass. Is the mass of the moth? Well, one molar mass of air. You would just go. I'm taking up. Yeah, so you have to go on. No, but I don't think she wants this. Okay. So we're missing something. Yeah.
Oh, okay, so the room's just a box, right?
Oh, so it's R.
The room,
Yeah, that's it. I'm getting it.
the volume.
The volume. Is it R just a constant?
Oh, and then I can
So I thought it was 831. Yeah, isn't that a constant? Yeah, so we are looking for. Okay, so yeah, we're looking for P. How we already have P. Where do you have P? P is the pressure of the room of the atmosphere. I think we're looking for we have the volume. The dimension. What are we looking for?
R. I got like fucking.
These are R for the two.
Oh.
I mean,
so
what is the person?
yeah, so that would
You guys, maybe we're looking for R. Guess it's just solving for R.
Pounds, right? So what about kilograms?
PV NT.
Less than
PV over NT.
of the mass.
I just did.
Which makes sense, right? You have to like smush all the molecules together. What do you get?
What are we using?
Yeah,
for
what
math?
did you-
You don't know.
What are we using for now? What are we using for math?
What are you solving for?
I think we have R, I think.
R is a constant.
Okay. So V, right? V?
N,
N?
right? If you know the number of moles of air, then you can figure out the mass of the number of moles of air. You have the molar mass. So with moles, multiply it by moles per kilograms per mole.
Wait, so the molar mass, how do you use that in the sense of plugging it in?
So we use it after you solve for moles.
Okay.
Right? You get the number of moles. That tells you how much air is in the room. And then you want to know the mass of that air. So you use the molar mass.
Okay.
Yeah. Yeah.
I don't. Eddie does.
Yeah.
Eddie does.
How much do you, what's your mass?
I don't know, dude. The empirical system is fucking up.
Imperial.
Imperial.
All right, guys. So, we're just estimating basically the gas in a box, okay? So, this dimensions of the room, that's just the dimensions of some sort of box, okay? So, we have 5 by 3 by 2.5. So, let's say, it doesn't really matter, 5 meters, 3 meters, 2.5 meters, okay? That means volume is going to be 5 meters times 3 meters times 2.5 meters, which should give you about 37.5 meters cubed, okay? We know the temperature here.
1555?
What?
1555?
That's moles, yeah.
Okay, well, and then you have to use that one.
Yeah.
Okay.
And then the temperature in the room is 20 degrees Celsius. What's that in Kelvin? 293 Kelvin, okay? The pressure in the room, yeah, you would know if it wasn't atmospheric pressure in here, hopefully, right? It would either feel like your ears were going to pop or something. So this is 101 times 10 to the third pascals, okay? So what are we solving for? N, we're fine. We want the number of moles. We use PV equals nRT. We want to solve for the number of moles. So PV over RT. So that's going to be 101 times 10 to the 3 pascals times the volume. The volume is 37.5 meters cubed divided by R, which is 8.31 joules per mole Kelvin, and temperature, which is 293 Kelvin. This should give you about 1,600 or 1,555 moles. Okay, and what does moles tell us? Yeah, what, like just the amount of air, right? The total number of air molecules, essentially. So we have the total number of air molecules, but we want the mass, so we have to know something about how much mass there is per mole. That's called the molar mass. So if we want the mass, we multiply N times the molar mass, which is usually indicated by a capital M, all right? And that's going to be this times 0.029 kilograms per mole, okay? That's going to give us about 45 kilograms, which, I mean, seems like a lot because we think of air as being light, but it's actually less mass than any one of you, essentially, okay? So if you smushed all the air together, it would still weigh less than a person, all right? Right now, the molecules are all just kind of like around. You can feel them, but they keep moving. Okay, so just to go through, the units. All right, here we have kelvins, right? We know moles is going to stay, so that means this is newtons divided by meters squared times meters cubed. Okay, so that gives you Newton meters. Newton meters is the same as joules, so that cancels, and and all we have is moles. Okay? Over here, we have moles and kilograms per mole. The moles cancel, you end up with just kilograms. All right, so just be careful with your units to make sure that you're using the right stuff. No, Jesus is not one of the units. All right. Let's try stoichiometry. You don't have to say stoichiometry in here.
I like chemistry. It's fun.
It's just applied physics. No, you can't be a rival if you're like a subset of something else. Hint, please think of this in terms of PV equals nRT. All right, we got about 9, 8, 7, 6, 5. All right. Oh, we have one more person. Okay. Just an okay. It's, well, you guys know it can be determined. Please discuss. We'll vote again.
I don't know. No idea. I've never taken chemistry, so.
Well, just look at the periodic table. Which gas is heavier?
Which is it? I think so.
Nitrogen. Right, so if you have equal mass, which one has more molecules?
I don't know. Student A.
Yeah, I think it's
I'm the only one. I don't really want to have the lighter gas.
Oh, no. All right. Yeah, we're taking it to 11 today. It's shifted. That's actually bad. Less people voted for the right answer. Okay, so let's think about what does it mean to have equal mass? Okay, because none of these. So we're looking at PV equals nRT. Okay, so PV equals nRT. What do we know is constant? R. Yes. R is constant. P and V are constant too. So we're only adjusting N and T. If N goes up, what happens to T? Has to go down, right? Because this has to stay constant, okay? So these have to always multiply to the same thing, okay? So if N goes up, T goes down. If N goes down, T goes up, okay? So larger N means a smaller T. Now how do we determine N? We know these things have equal mass, okay? What do we know about helium versus nitrogen? Helium is lighter than basically everything except hydrogen, okay? So we know helium is lighter, which means if we have the same mass, which one has a bigger N? Helium. Why? Yeah, you need more pieces of helium to get the same mass, right? Because helium's lighter, so you need more of them, more particles, that's right, that's the word, particles of helium to get the same mass as less particles of nitrogen. So that means your N for helium, bigger, okay? What does that mean about the temperature for helium? Lower, okay? So if we have more helium, it has a lower temperature, which means the temperature of helium should be lower than the temperature of nitrogen. Yeah, well, you can also, you can look at it that way too. No, because there's always going to be if it's the same mass, you're always going to have more helium particles than nitrogen particles. Do you see what I mean? So as long as your N is bigger, then your T is smaller. Okay. All right. Cool. Short. So let's talk. I mean, basically, when we're dealing with an ideal gas, we're making a lot of assumptions. If you want to get a little bit more complicated, you have to use this thing called the van der Waals equation, okay? Which is if we change these things so that they're no longer these little point particles, all of these little molecules have interactions, right, as they bounce around, okay? The size of the molecules is determined by this term. The interaction of the molecules is determined by this term. And this also takes into account the fact that molecules have a physical size. Right over here, when we talk about an ideal gas, we ignore the physical size of the molecules. And so we have to subtract that off the volume and all this other stuff. I'm showing you this. You don't need to memorize it. I just want you to know that it's a little bit more complicated than PV equals nRT. And here are the corrections.
What is it?
Okay. A is just a constant. So B represents the volume of a mole of molecules, right? So you subtract the total volume of the molecules from the volume of the container. And A represents the attractive intermolecular forces. So remember, molecules are usually made of atoms which have positive and negative charge, so you end up with forces that interact with each other. So you have to get rid of the pressure, you have to subtract off the molecular interactions. To fix the volume, you have to subtract off the actual size of the molecules.
So is N still moles?
And still moles, right? This is still pressure, volume,
So
nRT.
it's a constant.
So this is still PV equals nRT, but we're correcting pressure and volume for like real world things. Okay, and just like we've said before in physics is we start with the simpler model, right? We start with the simplest model, and if that doesn't work, we add back in the complexity. Okay, and here is some complexity. All right, we're not going to do anything with the van der Waals equation, but I would like you to see it because if you go on in engineering, it sometimes comes up. So now you've seen it. Okay, especially in like material science. All right, so let's talk PV diagrams. Okay, so let's say we pick a little point here. What can you, now that we know that we have PV equals nRT, let's say we have a sealed container.
Is that
Okay, so what's, yes, kilopascals. So what's the volume of this thing? 3 meters cubed. What's the pressure? 10 kilopascals. So 10 times 10 to the third pascals. So about 10 times less than atmospheric pressure, right? That's the one. Yeah. Okay, what else can you figure out about it? Let's say we know there's 1 mole of this gas. Yeah, you can figure out the temperature. Okay, so how would you figure out the temperature? Yeah, you plug that shit in to be to be specific. Okay, so this point represents a particular state of the gas, and we know it's a state because we can figure out all the state variables. We have P, V, and T. Okay, just looking at this graph, you can figure out the state variables as long as you're given the number of moles. All right. Then over here, let's say we have the same number of moles. We have a new state. Okay, and over here we have another state. And if we want to go back and forth between the states, that means moles and R are constant, and so that means these things are all related by this. Okay, which is just saying, you know, these are all going to be equal to NR because it's 1 times 8.31. So all of, when you multiply PV divided by T for all of these, they should just give you 8.31. Okay, so they're all equal. So when you're going back and forth between these states, all right, on a PV diagram, you can figure a lot out just looking at the graph. Okay, and so we can figure out the temperatures. This one's 3,600, this one's about 900, this one's about 600, so this one's really hot. And you can see the temperature as you move this way gets hotter. As you move this way, it gets colder. Okay, and we'll see what that actually looks like in a minute. But the other thing about a PV diagram, these give you the states, but when you use a PV diagram directly, it should tell you how you get from state to state. Okay, and I'll show you what that means. okay? For this, if we're in state 1 and we want to get to state 2, any lines that connect those 2 points are considered possible, okay? But here's 2 different ways you can get there, all right? In this case, you have an isochoric, right, constant volume, right? You change just the pressure, and then you change just the volume, okay? So you're passing through some temperatures, but these temperatures are all going to be less than 900 Kelvin because you're going this way. If you go this way, you've done some other shit, and you go through this crazy temperature, okay? In either case, you go from this state to this state, all right? You start and end at the same place, but the way you get there is going to vary dramatically, okay? There's lots of different ways to get from one state to another, and it matters how you do it, okay? All right. So let's talk about the ways, the standard ways. So any line is possible, but there's some standard ones that are easy to understand and come up a lot, okay? So we'll start with an isochoric process. What does isochoric mean? Yeah, it's constant volume. It's the least easy to remember because nobody knows what choric means. It's probably Greek or Latin.
It's probably Greek.
Everything's Greek. It's all Greek to me. So let's say we start with a fixed volume, okay? So how do we usually get a fixed volume in the real world? A sealed container, right? A container that doesn't change shape. So like a balloon, not a great way to get fixed volume, okay? But actually, what does a balloon keep? Pressure, right? What's the pressure inside a balloon when you blow it up? Yeah, 1 atm, right? You have to keep the pressure on either side of the balloon has to be equal or the balloon changes shape, okay? So when you have a balloon blown up, you can assume the pressure inside the balloon is 1 atmosphere because the pressure outside the balloon is 1 atmosphere, okay? And if you change the pressure of the air in the balloon by cooling down the molecules, then you still keep a balance of the 1 atm, right? It changes the volume and you get back to 1 atmosphere, all right? So the pressure inside and outside of a balloon has to be the same. If you put a balloon underwater, what's going to happen to it? It's going to pop. Why? If it's sealed. What happens to the pressure as you go underwater?
Oh, yeah.
It increases, okay? Yeah. So you have to actually, so this is why airplanes and submarines and things are pressurized, right? If you go up in an airplane, what happens to the pressure of the air? It's lower, right? Yeah, so you have stress, you have forces acting on the outside of your plane because things are trying to push out, okay? So you have to have strong materials or you have to equalize the pressure. You don't want the pressure inside your airplane to be the same as the pressure outside because why? Yeah, you don't want to die. So, because, well, it's cold. That's not the bigger issue. You can heat it up. But you need a certain amount of density of oxygen in the air so you don't die. And if you get to the pressure that's outside a plane, that's not enough oxygen for your whole brain thing to work. So that's why when you summit like Everest, you have to take your own oxygen with you in a can because at the top, it's not atmospheric pressure anymore, right? It's thinner air, less pressure, so less oxygen, more dying. Okay. What? Yes, yeah. Colorado has less drag, right? All right. Okay, so anyway, constant volume, you have a fixed container, all right? So here, let's say this is our volume here. We have some pressure at pressure 1. Now let's add some fire to the same. These were the same to begin with. Now we've increased the pressure, okay? How do we increase the pressure? Well, we raised the temperature, kept the volume fixed. That means the pressure has to go up because we can't change the number of moles. It's trapped in a container. R is a constant. The only thing that can change is the pressure. Okay? So here is our pressure 2. But what do we notice about the volume? It's constant, right? If it's along a vertical line, we have not changed the volume. And so how would you describe this process? Isochoric. You go from pressure 1 to pressure 2. Okay? And if you took this and cooled it back down to here, you just go back down. But the arrow is important. It tells you where you started and where you end.
Isochoric describes the constant volume. So how would you describe that movement? Is it also isochoric?
Yeah. Just isochoric process.
Even if it went in reverse.
Isochoric, this would be an increase in pressure, a decrease in pressure would also be isochoric, as long as it stays along a vertical line. Yes. Okay. Here's a question.
Is there a barrier between the piston and the container? Is it like a wall, or is like the piston part of the sealed container?
It's like floating on top of the gas. And I mean like over like the long period of time, not like immediately. Okay. So most we think it will increase. Let's discuss. Now remember, over a long period of time, okay?
I'm understanding the question. I don't know if I
Unless it's not, I think that's over a long period of time.
So I think that is like part of like
Well, it's going to increase, and then what happens?
it's
Over time,
it'll go to equilibrium.
They're increasing volume. So that means the pressure.
Not a well-worded question. But if you increase the
What's going
temperature,
to happen is that mass,
what happens
that piston's going to evolve.
to the gas? Pressure increases,
Yeah.
right?
Pressure is
And then what happens to the volume?
basically since you expand the volume.
Yeah. Because if the pressure inside the piston is bigger than the pressure outside the piston, what happens to that little piston?
It goes up.
It goes up, right? And then what's the pressure?
Equal to
The outside.
Yeah.
Right? It's going to move until it's equal to the outside. Okay. So let's start. Vote again. Perfect. Better. D. Huh? That's actually a decent answer. So nothing's going to happen over time. Because what's going to happen instantaneously, right, is you heat up the gas, and we know that's going to increase the pressure of the gas. Okay? Well, if the pressure inside is bigger than the pressure outside and the piston's free to move, what does the piston do? It goes up. Okay? When does it stop going up? When the pressure is equal again. Okay? And so that means this gas, as if you do this slow enough, is always going to be at what pressure? 1 atmosphere. Okay? It's going to maintain 1 atmosphere. Now, it'll fluctuate a little, right? It'll go up and then it'll move, and it'll go up and it'll move, but it'll happen pretty fast. So this way, as long as you don't heat this thing up too fast, this is a way to always keep the pressure the same. All right? The pressure inside has to equal the pressure outside because you're just balancing forces. Okay? Anytime there's more pressure inside, it just moves the piston until the pressure's the same. Okay? And so we call this an isobaric process. Okay? Isobaric process means constant pressure. Okay? And just to break down the forces, since we love force diagrams, if you look at the piston from the side, it has weight, okay, mg going down, and then it has another force going down from the air sitting on top of it, okay? So remember, pressure is force over area. So if you want force, you take pressure times area, okay? So force over area times area, you get force back, okay? So this is going to be atmospheric pressure times the area, the cross-sectional area of the piston, okay? Going up, you have the pressure of the gas times the same area, all right? That means if you have a movable piston, you can just write this as a force equation, right? We know that P times A minus mg, that's a force equation, right? If you add up the forces, you have this minus this minus this. Okay, we divide through by A, you get something that looks like this. All right, and what this means is as the temperature of the gas increases, the piston's going to move so that this becomes equal again. All right, so a movable piston ensures constant what? Pressure. Okay, so as the temperature increases, the volume of the gas increases in order to keep the pressure constant. All right. Wait, what? Capital A is the cross-sectional area of the piston. Okay, so it's not quite that the gas. So if you have a massless piston, then these two things are equal. Okay, if you have a piston with mass, then your pressure is going to depend more on the mass of the piston plus the pressure from the outside. Okay. Gravity. Yeah. Acceleration due to gravity. Yeah, this is the mass of the piston. I know, it's like sometimes we use it for molar mass. This is the mass of the piston. Okay. This is G. This is the cross-sectional area of the piston. All right. But as long as you have the same mass, you should have the same pressure. Okay. So let's look at what this looks like. So we have constant pressure. Okay. Here's our first situation. That guy has volume 1. Okay, volume 1, that's the pressure. The pressure depends on the mass of the piston and the atmospheric pressure. Okay. Then we add some temperature. Right? What do we know about the pressure? Constant, right? Because we have the same piston, but the volume changed. So this is an isobaric process, and this would be called an isobaric expansion. How do we know it's an expansion? The volume got bigger, okay? So if you go this way, it's an expansion. If we went this way, what would it be called? Compression, right? So isobaric compression, all right? So as long as we have a movable piston, we get constant pressure, okay? Movable piston means constant pressure, all right? Yes. Constant explosion. Okay. So we can solve. Yeah, let's do this one. It'll take about 5 minutes. Just want to make sure we get through everything.
don't think so.
So you have two states this time.
Do you, what do you
So like here.
Oh, I see.
Yeah. So PV equals nRT.
Yeah.
What that tells you is we know this is constant, right?
Mm-hmm.
And these are constant. So let's bring all the constant things to one side. Okay.
Okay.
That should be equal to T over B.
Okay.
Okay. So T1 over V1 and also T2 over V2 because this should be constant no matter what you do to these two things.
Okay.
Right? Because this is a constant, this is being held constant, and this is just a constant. Okay. So that means we can ignore this and just use this.
Oh, okay. Okay.
So those pressures
Oh, here's a fun thing. P1 is equal to P2. So yes, they do.
Yeah.
Perfect. So you can throw what's constant? R. P. So that means P over N R. This whole thing is constant. And it's equal to P over V. Okay. So we can so let's say we throw T1 and V1. That's always equal to this. Right? Because this doesn't change. If we heat it up, that's T2. That should also be equal. It's a different volume, but it should also be equal to that because it doesn't change. So now you can just deal with this.
Oh,
Yeah. So you do start with people who have NRT, but it gets constant. Yeah. So anytime you have constant pressure, you can use this. This is just the derivation for that. Okay. If you had constant volume, right?
switch out the V.
That would be P. What's going to happen with pressure? It doesn't actually show up in the equation. What's this in meters cubed? So you left this in centimeters. Oh, did you? It's not 0.5. If they were centimeters, though.
Oh yeah, that's right.
So you have like, but the other thing is for this, you can see with different units, right? So you need to convert centimeters. And just leave it in centimeters. So just leave it as 50. Because if you convert 50 centimeters to meters cubed, it's going to be 5 times 10 to the negative 2. Let's talk about that. Let's see.
I think I did this completely wrong.
I got like 43.
Yeah, I don't know what I'm getting. Think of it. What are you getting? 10? No, of course that makes sense.
That makes sense.
Of course that makes sense. That is the dumbest thing ever. What? 10.
What about it?
It is not. Yeah. Okay, it is 10.
Okay. That's just what I did right there.
I know, I was looking at it because it's 50 over 50. I converted it into,
Yeah,
and then we just took a look. And then
that makes sense.
that is so ridiculous.
So before we even start, should the volume be getting bigger or smaller? Smaller. Why?
Because temperature's cool.
Yeah, temperature is going down, so we know the volume should be decreasing. Okay, so this would be an isobaric compression. Okay, isobaric compression. So our answer should be less than 50 centimeters cubed. Okay, so let's go through this. We can start with PV equals nRT. Which of these things are constant? P
and R.
and R is always constant, and N, right? Because this is we're not changing the gas that we're using. Okay, so it always has to have the same amount of gas. So that means P over NR is going to be equal to T over V. Now this whole thing, let's say this is 6. Does it change if you change the temperature? No. Okay? So this, if you start with T1 and V1, has to be equal to this. And later, if we decrease the temperature, it's still equal to this because this stuff doesn't change. We know the pressure stays the same, we know R stays the same, we know N stays the same. Okay? So what I want you to take out of this is any time you have an isobaric process on a PV diagram, okay, this is true. We have this ratio instead of this whole big thing. Okay? So we're going to use this ratio to solve for our new volume. All right? The other tricky thing is, what do we have to do for the temperature?
Convert it to Kelvin.
It has to be converted to kelvins, okay? Because you can't, since it's a ratio, you can't be off by a fixed amount. That'll ruin your fractions, okay? So in this case, because it's not a temperature difference, it's a temperature ratio, you have to convert to Kelvin, okay? So we want to solve for V2. V2 is going to be T2 over T1 times V1. Okay, we just did some quick algebra. So that means T2 is 10, right? So what is that in Kelvin? 283 Kelvin. Our T1, that was 50 Celsius, so that's 323. All right, this is good. This fraction should make our volume smaller. And this is gonna, we can leave this as 50 centimeters cubed. Now, why can we leave it? Yeah, our answer is gonna be in centimeters cubed, and the change of meters cubed to centimeters cubed is a constant multiplication factor, not a constant addition factor, right? These, you add 273 to both of them, so that would change the fraction. But if you multiplied them both by something, that would cancel. Okay, so we don't need to convert the centimeters. You can, and if you convert centimeters to meters cubed, what's an important thing to remember? How many centimeters cubed are in a meter cubed?
300.
What? How many centimeters cubed are in 1 meter cubed? It's not 100. 100 to the third, right? What's 100 to the third? 1 million? Okay. A lot more than 100, okay? So remember that when we convert by cubes, that's going to be 10 to the 6th, not 10 to the 2, all right? So anyway, this should give you 43.8 centimeters cubed.
Oh, right.
Yes.
If you use the 0.5, the math's still coming out the same.
Right, but you'll have the wrong point 5 won't be the it doesn't it's not the right value.
Right.
It would be incorrect. I mean, it'll convert properly. Like whatever you start with, you'll end up with, but it's not going to give you the right numbers because 50 isn't 0.5, right? So 48 isn't 4.8. Yeah. Anyway, okay. Let's take a break. Come back in about 10 minutes.
I didn't do any of that.
Any of what?
I'm always like finding answers without doing algebra. Gets me in trouble a lot.
Does it work?
Yeah.
That's I mean, as long as the answer's right, I don't really care.
It's not that I'm like puzzling, it's just like the background. It's only when you're far, it's like when you're close to it, you can see, but I had to take like a class on it was like, I didn't know either. And depending on what the background color is, you gotta change it. It's like a color of text.
We're back. Question. All right, you got about 5 more seconds. Just hanging out. Okay. All right, let's discuss and we'll vote again.
Are they the same gas?
Doesn't matter.
Right?
That makes it a lot better.
Because the volume is different, but the temperature is the same. The pressure is different.
The pressure is higher.
The pressure is the
Well,
higher.
the temperature is the same.
Yeah. No, the temperature is the same. Pressure is different.
Right.
So the pressure is going to be higher in gas too.
So good.
Yeah, see.
The pressure.
The pressure could be higher on gas too. Temperature is the same.
These are 2 different canisters. They just have the same mass piston. Okay.
Can't be determined.
All right, guys. Lost somebody. Oh, okay. So, how do we determine pressure? Remember, if we do the force diagram, pressure should be the atmospheric pressure plus the mass of the piston. Does it have anything to do with the gas? No. Okay? So as long as the mass of the piston is the same, and they're in the same room, what do we know about the pressure? It's the same, right? The volume might be different, okay? You can see the volume's different. The number of moles might be different, but pressure is determined by the atmospheric pressure and the mass of the piston. If those are the same, then the pressure is the same. None of the other stuff matters. They don't even have to be at the same temperature. That was just misleading, okay? The only thing that matters for the pressure is that the outside pressure is the same, and the piston has the same mass. Okay?
I have a question. How, if they were the same exact gas, how could they have different volumes?
They could have more moles. They have more of the same gas. Yeah. Okay. Okay. Another question.
Equilibrium meaning that it tops off.
Means that it stops moving. Okay, let's discuss. We'll vote again. We're gonna have to keep doing these questions till you get them right.
Until we get them. We started out so strong. We're so
Me too, but makes sense because it's already at equilibrium right here, or state. So if it increase and it reaches an equilibrium, the pressure is still the same. So
Yeah, what does the pressure depend on?
It depends on atmosphere.
Which is the same.
That's not a good question. That's what I thought. I don't fucking know.
The mass of the piston. Mass of the piston. Yeah. Okay. Please vote again. Perfect. Better, except for two of you. So, what does the pressure depend on for the gas? The mass of the piston and the atmospheric pressure, which are still the same. It doesn't matter what you do to the gas. Once it reaches equilibrium, right, the pressure only depends on the outside pressure and the mass of the piston. Okay? So that's going to be pressures are equal. Yes?
So if these containers were closed, sealed, this would be
Isometric isn't a word that we've learned today.
Isochoric, sorry.
Yeah, if the piston can't move, then it's isochoric. But if the piston can move, then obviously you can change volume, and it's isobaric. So a non-moving piston, a fixed container, is isochoric. Something with a moving piston obviously can change volume. Yeah, so that's isobaric. Okay. Wait, I think this is the same question. Is that the same question?
Yeah.
Oh, to the no. Okay, let's whatever. All right, basically, the result of this is that you always have your pressure of your gas dependent on the mass of the piston and the outside pressure. Okay, once you reach equilibrium, it only depends on how much your piston weighs and how much atmospheric pressure there is. Yes?
would it be different if it was in like water?
As long as they're both in water,
Okay.
doesn't matter. Yeah, they have to be at the same depth. But yeah, as long as the outside pressure is the same, it doesn't matter what's causing the outside pressure. They should be the same. Okay? All right. So let's talk about the guess what isothermal means? Same temperature, constant temperature, okay? Not constant heat. Heat can move. So isothermal means constant temperature. So let's say, why are these things in this lovely water bath? So what happens if you throw something in the ocean? What temperature does it reach? Whatever temperature the ocean is, okay? If you wait long enough, you get thermal equilibrium. So if you have a large body of water, like a water bath, that can regulate your temperature, okay? Even humans, if you stay in the ocean long enough, will reach the same temperature. You'll be dead, but you'll reach the same temperature of the ocean, okay? Your body will burn calories to stay at the temperature you want to be at until it runs out of energy, and then you die. Okay, so we start with this temperature, and then what we do is we slowly press down on the piston, right? So you have to apply an external force. So So you're decreasing the volume, okay? So you're changing both the pressure and the volume, and you can see you're changing both pressure and volume until you get over here. Now, this line, what do you know about this line? What's the same on this line? Temperature, okay? So isothermal processes aren't straight lines, they're these curves, all right? And everything along this curve has the same temperature. It's the temperature of this water bath. Now, how do you maintain the same temperature? Well, you have to do this process very slowly. So basically, you change the pressure and volume, but you wait for it to go to the same temperature, and then you do another step. So it's a very slow process. Okay, so isothermal processes must happen slowly. Okay, so yeah. And it turns out, so that's an isothermal compression. You can also have an isothermal expansion, okay, which is going the other way, and that means it's going from a smaller volume to a bigger volume, okay? Expansion just means smaller volume to bigger volume. Compression means bigger volume to smaller volume. So if you're going this way, that's an expansion. If you're going this way, that's a compression. So it just depends on the arrow, okay? Now, isotherms look like this. They're these curves, and they look like an inverse. Guess why? Because they are an inverse. Because if you think about PV equals nRT, right? If you're looking at the T diagram, the T part of the diagram, okay, that's going to be an inverse. So P, if you keep, sorry, I said that badly. If you keep T constant, that means you have PV equals nRT. This whole thing is a constant. Okay, so your graph looks like P constant 1 over V. That is an inverse curve. Okay, this is your Y, this is your X. This is like saying Y is equal to some constant 1 over X. All right, so you're going to get an inverse. If you increase your temperature, okay, then your isotherm moves that way. If you decrease the temperature, it goes the other way. Okay, so it goes hotter this way, cooler this way. All right, so temperature increases as you move away from 0. Okay, cooler is closer to your axes, hotter is farther away from your axes. All right, here's this is for an ideal gas. Just for some comparison, this is for a non-ideal gas, right? Because remember, it doesn't stay a gas. So here's where it's a liquid, here's where it's liquid and vapor, here's where it's gas, okay? And this is what your curves look like. They're all messed up. Yes, they depend on the state, right? And you can see when things are liquids, it behaves differently. But you can see, here's the ideal gas part, right? Because remember, we said ideal gases have to be far away from the condensation point, which is somewhere over here. Okay, if you get close to the condensation point, you get all these little kinks in your curve. If you're far enough away from it, you get these lovely isothermal curves. Okay, so just some food for thought. All right. Okay. Here's a question. Let's say no, you both it.
I just gotta make sure, otherwise Eddie will press it for me.
Yeah, bro. See,
It's not me, Daddy.
All right. We lost somebody.
No,
All right. We tried. We're doing better. The same 8 people are convinced, I think. So I'm just going to say this is B, okay? Because remember, what determines the pressure? outside pressure and the mass of the piston. So if you want the same pressure, you need the same piston. Okay. All right. We're gonna come back to this. We're gonna do this. We're gonna do this problem together because we're running out of time. All right. Let's do this. So read the question while I erase this. Okay. So we have 1 mole of ideal gas. Okay, initially at standard temperature and pressure, undergoes an isochoric increase in pressure until its pressure is doubled. Okay, so before we even start this, okay, let's start with our first point. So we'll call this
So did I miss
P1
what STP means?
and V1. STP? Well, it also means Stone Temple Pilots.
No, really, I don't
That
know
guy's
what
dead.
it means.
He's dead.
He is. Very sad. Yes.
No, really don't know what STP is.
Oh, standard temperature and pressure.
Oh, okay.
Sorry. Yeah.
It
doesn't mean Sorry, I shouldn't answer questions with a joke. I should answer them with answers. So we start with at standard temperature and pressure. That means we're here. We're at and remember, 1 mole of gas at standard temperature and pressure. Do we remember what the volume is? We just did it, but we're not going to do that again. So V1 is 0.022. Remember when I said remember this?
Oh yeah.
And that's meters cubed. Oh, yeah. Let's do this in kilopascals. So what's pressure one?
It's just 1 atmosphere.
1 atmosphere, so 101 kilopascals. So yeah, times 10 to the third. So pressure 101. So we start here, okay? And then it undergoes an isochoric increase in pressure until its pressure is doubled, okay? So that means we end up here with pressure 2. What should pressure 2 be? 202. And what does isochoric look like? Well, it's going to be a nice vertical line. So here's state 1, state 2. Okay, this is 1, this is 2. Okay, and what's our volume? Yeah, it's still 0.0224 meters cubed. Okay, all right. It then undergoes an isothermal expansion until its volume is doubled, and then an isobaric compression. So isothermal expansion looks like this. You have a nice inverse curve. Okay. So this is your isotherm, and it's an expansion because your volume is going from something smaller to something larger. So we know whatever the temperature here is has to be equal to the temperature here. This is temperature 1 here. Okay? And it does that until its volume is doubled. So what's the volume here?
0.0448.
Yeah, that's going to be 0.0448. And then it undergoes an isobaric compression. So what does that look like? Horizontal line, right? Until it returns to its initial state. This is also 0.4. Okay? So here's our PV diagram for the process. And we know the pressure and volume at all the points. So all we have to figure out are temperature. Okay? So we'll start by figuring out temperature 1. Okay, so we just use PV equals nRT, and we solve for T. So PV over nR, P1, V1, P1. Okay, so pressure 1, that's 101 times 10 to the third pascals. volume 1 is 0.0224 meters cubed, and this is N 1 mole, 8.31 joules per mole Kelvin. So that means our temperature should be temperature 270. Oh, it starts. We know what temperature it starts at. Should be 273. Sorry, 200. But hopefully that still gives you 273.
STP for the win.
Yeah.
Don't tell the cards.
All right. So then we undergo this. Wow, that was a given. All right. Then we undergo this isochoric process. Okay. What's the ratio we use for an isochoric process?
Oh, is that P1?
Yeah, V1 over T1 is equal to V2 over T2. Okay, so we want T2. That's going to be V2 over V1 times T1. And remember, V2 is just twice V1, so it's 2 times 273 Kelvin. Very simple math on these. 2 times 273 gives you 500 and stuff. 546. Okay, so that's T2. T2 is 546 Kelvin. What's T3? Should not have to do any math to get T3. What do you know about this line? What do we call this?
It's the same temperature.
Isothermal, which
Still
means it's the same
546
temperature. This temperature is the same everywhere
So it's still
along this
546.
line, which means it's also the same here. So that's 546 Kelvin. And then guess what the temperature is here? 273. Okay? So these PV diagrams, it's just solving a puzzle. You're trying to fill in the blanks. Okay? So yeah, you're just using PV equals nRT to solve for all the little points. All right? Okay. So let's talk molecular properties of matter. We could probably skip that actually.
Wait, what's in that?
Here, we'll just go through it quickly. So remember, here's molecules in an ideal size. Okay, so this is like our ideal gas. Okay, real molecules go from little tiny spheres all the way up to giant multi-atom structures, right? So you can have like a little bit of helium gas, or you can have giant paraffin molecules that are long chains. You can get like all these crazy organic compounds that are like folding proteins. That's still a fucking molecule, okay? So you can go from little to big. You can do this, okay? There's all kinds of stuff. So the other problem is sometimes molecules have charge, and that affects the spacing of the molecules, because if your molecules are attracted, they're going to end up closer together. If your molecules are repelled, they're going to end up farther apart. So it's not just the same as atoms that are diffusely just bobbing around in space, okay? They also, this is the distance between them, okay? Turns out if we have a force that looks like this, we have some sort of energy, potential energy that looks like this. So the force, this area, this is the equilibrium distance between them, okay? It's at the minimum energy, because remember, everything likes to have a minimum energy, okay? So here's your minimum energy, and that's where your equilibrium distance is going to be, all right? And you don't necessarily have to remember this. I'm just showing you how the stuff we've learned before applies to this, okay? So for instance, if you are at this point, all right, here, your distance is farther away, right? It's larger than your equilibrium distance, okay? That means you're somewhere over here. So R bigger than R naught, okay? If you're at equilibrium distance, if you're less than here, they're going to be repulsive. So, okay, if your atoms are far away, they end up being attracted if you have charge, okay? If your atoms get really close together, they end up being repelled, all right? If your atoms are at equilibrium distance, then they just hang out there. So you're going to have this push and pull of forces depending on the distance between your atoms, okay? So your total energy, right, ends up determines how your atoms behave. And the total energy usually has to do with the thermal energy, Okay, the temperature of your gas tells you your total energy of your system. So if you're here, what do these atoms do? If you're at this total energy, right? You have this R max, R min, this is your energy curve. What's happening to these atoms? Well, you put a little energy in, they jiggle back and forth, okay? Because remember, anytime we have an energy system that looks like this, that looks like our spring, okay? If you have an energy curve that looks like this, then they're going to go back and forth across your energy curve, okay? So if you start with more energy than you have at equilibrium, they oscillate, okay? Are those things still oscillating? Well, they're not. But you have R min, R max. You put in some energy, they can get closer than equilibrium, and then they bounce, they repel, and they go back and forth, okay? All right, so that's how molecular charge affects gases, okay? So it's a little more complicated than the ideal gas situation, because remember, ideal gases not charged because they're mostly on that nice noble gas neutral range, okay? Yeah, so here we have oxygen, right? Yeah, anyway, this is just atomic mass number. Do you guys are familiar with this? No? Kind of?
Why wouldn't
Okay.
you just round up to make oxygen 16?
Oh, it will be. But so we're just talking about water here. All right, so water, H2O. That means you have an oxygen. Oops. Oh, you have oxygen and 2 hydrogen, and these are your atomic mass number. That's the number of protons plus the number of neutrons, but it just gives you your total mass, right? So you just multiply that by your grams per mole. All right. Anyway, you can figure out molecular mass, like for water, that's going to be 16, right? And plus 2, so 18. All right. Because remember, 8 is the number of protons. You have to include neutrons, so you double it. Okay. All right. Moles look like this. Yeah, that guy. He's a real. He kind of looks like a lizard.
Finally, he looks like a lizard.
Yeah. So anyway, molar mass is usually capital M, although sometimes we use that for mass. Just make sure you use context clues to figure out what you're doing. That's just the mass of one particle times Avogadro's number. And why do we care about having a mole of atoms? It's easy to measure the mass of one atom. No. Okay? If you want to figure out how much each gold atom weighs, you get a bar of gold and then you divide by how many moles of gold you have, and then you use Avogadro's number, okay? The reason we even bother with Avogadro's number is because atoms are really freaking small, all right? All right, let's talk about the kinetic molecular model of an ideal gas. Oh, just word to the wise, that problem we did, this last one, yeah, this is the sort of question that will be on the test, okay? So we have calorimetry and this one, calorimetry, and there's 4 possible questions that I'm going to tell you can be on the test. We've already done 2 of them, okay? So calorimetry, PV diagram. Yeah. Calorimetry has to do with MC delta T. What? That one? That specific one? That would be so nice, wouldn't it?
That would be so nice.
I don't know how nice I'm feeling. Okay, we're gonna skip this microscopic thing and talk about heat capacities because these are important. So let's talk about degrees of freedom. Okay, if you have atoms, here's the ways you can store energy. Okay, because remember thermal energy is microscopic kinetic plus microscopic potential. Okay, so remember kinetic energy. So far we have 2 kinds. We had translational and we had rotational. So 1/2 mv squared, 1/2 I omega squared. We don't need to remember that for this. But here, translational, you translate along x or y or z in a straight line. Okay. Rotational is if you rotate. If you do both, then you include both. Okay. Now we also have vibrational. That goes like this. Okay, it's just jiggling atoms. All right.
So vibrational, but that doesn't actually it just stays in place and jiggles.
Yeah.
So what are you measuring? Just like the amount of
Yes. Jiggles per second. And then potential energy. Oh, so each of these, right, has 3 degrees of freedom because you have x, y, and z. So you can translate in the x, y, and z direction. You can rotate along your x, y, and z axis. Okay? And then you can vibrate in the x, y, and z direction. So you can vibrate like this. You can vibrate like this. You can vibrate like this. Whatever. Okay. So all of them have three dimensions. All right? Potential energy. That's any type of intermolecular forces, so spring or electromagnetic, anything that has some attraction or repulsion, okay? And of course, that is times 3 because you have 3 dimensions. Okay, so all of these are 3 dimensions. So this brings us to something called equipartition theorem. So for each degree of freedom, right, there's an energy per mole of 1/2 RT. And R is just the 8.31 joules per mole Kelvin, okay, and T is temperature in Kelvin. So you can see that for each thing you end up with joules per mole. So a certain amount of energy for a certain amount of molecules, all right? And then each degree of freedom has an additional heat capacity of 1/2 R, okay? So that's just 1/2 times 8.31. So for instance, if you want to figure out the heat capacity, right, that's just going to be x, the number of degrees of freedom, divided by 2 times R. All right? And here's a list of our standard heat capacities. So for monatomic gases, right, monatomic gases, can they rotate really? Does it matter if they rotate? No, they're pretty much spherically symmetric, so rotation isn't counted. Okay? So that means you end up with just translation. How many degrees of freedom of translation do you have? 3. So 3/2 times 8.31. Guess what that gives you? What's 3/2 times 8? No. 12. Hey, look. 3/2 times 8.31. Okay? So that's 3/2 R. For diatomic, you have, so let's actually have a whole slide on here. So monatomic gases can translate in the x, y, and z direction, so you have 3/2 R. So translational times 3 looks like this, okay? Diatomic, you can translate in x, y, and z, and you can also rotate. You rotate in this direction. You can rotate around the x, you can rotate around the y, right? So you can rotate like this, you can rotate like this, but if you rotate like this, it doesn't really matter because it's hard to tell. So you only get 2 from rotation.
So heat
Okay.
capacity is C subscript V?
Yeah.
Okay.
That's the
Why
heat
V?
capacity for a constant volume.
Okay.
And that's the easiest one to measure because you just put it in a constant volume. So anyway, here's how many degrees of freedom do we have here? 5. Okay. CV, that should be 5/2 R. 5/2 R should give us about 20. And you'll notice for all the diatomic gases, our specific heat is about 20. Okay? It gets a little bit crazy, like vibrational motion can contribute. So like you can see for hydrogen, as you get up to higher and higher temperatures, right? So here you have what we picked, like 3/2, okay? So if it's really cold, you only get 3/2. As you get hotter, you get to 5/2. You can get all the way up to 7/2 if you get hot enough that vibration starts to matter, okay? So it's a little bit more complicated than what we're saying, but it depends on the temperature. And this is in the normal range of temperatures because you can see this is about 0, all right? 273, it's about freezing. If you go all the way down to, this is like really freaking cold because this is in Kelvin, okay? So this 3/2 doesn't matter too much for most cases. And then up here, this is like the temperature of the sun, okay? So it doesn't matter as much either, all right? For solids are, you can think of as the little molecules connected by like some kind of force, usually as spring force because they can vibrate a little bit. So you have this vibrational, and you have something like elastic potential energy. These should each be times 3, okay? So that should be how many degrees of freedom? 6. So you get 6/2, and that's about 3 R. And it turns out these are our solids, and at these temperatures, you can see they all get close to like 3 R, except for maybe diamond. Diamond's weird. Because it has like a really nice crystal structure, and so extra weird things happen.
I know, but like everything else on there is like an element.
Diamond's just made of carbon.
I know, that's what I'm saying. Why isn't it just like
Because it really matters for a solid, it really matters what the structure is. If it's a gas, it doesn't really have a structure, but for solids, like if you have carbon like pencil carbon versus diamond, they behave really differently, even though they're made of the same atoms. Okay. Oh man, I think that's all we got time for today. I know you guys are crushed. The rest of this stuff is interesting but not super important, so I'll post the slides with the solutions and everything. And we'll start the next chapter on Monday. After Thanksgiving.
The Monday, right? After.
Yeah, the Monday. Yeah. It's probably gonna be take home.
Okay.
Do you guys have a problem with that?
No, not at all.
Because you guys have 2 less labs than the other class, so they'll have to take it in person, but you guys will probably have a take-home test for the next test.
what was the color
That's what we did in the lab. Oh wait, have we done that yet?
You know,
Oh, that's what we'll do in the lab on Monday.
we're in integrals now. In calculus. And we're like, oh my god, I wish we would have taken this, and it would the first part of physics would have made
Like,
so
so
much sense.
So much of the physics all of a sudden like a light bulb clicked, and I was like,
Oh my god.
Well, that's good. It's before the final.
yeah, before the final. I mean, don't get me wrong. There's a lot of stuff we learned in this class. I just, wish it would have gradually, instead of like all together.
Yeah. It's hard though.